Hey guys, today's video is going to be over a couple different topics, and it's really going to really what I like about today's lesson is that it really shows a lot of the relationships between sort of physics or science and math. A lot of times you do things in math and you wonder, how is this ever used? But the answer is that math is really a sort of formalized way of understanding the world, right? And you can ask the philosophical question, is math invented or is math discovered? And that's not in the scope of this class. It's interesting to think about, though. So I like math. I think it's interesting to see how math can help us understand things that are happening, in the world. And that's really what physics does, right? We take math and we use that mathematics to understand the world. Or you could phrase it as our attempt to understand the world ends up being mathematical. So it's a philosophical question there. But today we're going to talk about graphing motion and sort of visualizing motion and seeing what kinds of discoveries we can make from that. So very first thing we're going to do here is I just want to talk about slope between 2 points. Hopefully you remember the equation for slope. I'll move myself up here so I'm not in the way. You remember the equations for slope and stuff. If you don't remember, slope is it's the change in, and a lot of times you'll hear as rise over run. Well, one way you can talk about that is the change in the y coordinate, rise, divided by the change in the x coordinate, run. And we use m to represent slope. I have no idea why. You can ask your math teacher and tell me, or you can Google it and tell me. I don't know. It's just the kind of what usually gets used. And let me be clear here. When I say delta y over delta x, it's a little confusing. This is the y coordinate here. This symbol, even though it's an x, this is the y coordinate. This symbol stands for displacement. And this is the x axis. This stands for time. So we could find this as delta y over delta x. That would be, remember when you take the change in something, you have to do final minus initial. The order matters because we're subtracting here. So it's last minus first, right? That's how you find your change. If I ask you how much have you grown over the last 5 years, you would take your height today minus your height from 5 years ago, and that would be the change there. So in this case, that would be y2 minus y1 would be x comma y, right? I sometimes have to say it out loud so I don't get confused. X comma y, so it would be 8 minus 4 divided by x is 5 minus 2. All right, and you would get 8 minus 4 is 4, 5 minus 2 is 3. You get 4/3. That's the slope here, 4/3. But let's think about this for a moment. What is this actually representing? What if instead of just having 5 and 8 and 2 and 4, what if we actually put units with that, right? Let's assume these are the standard units. So the x-axis, right? The x-axis is down here, right? This is the time axis. So instead of 5, let's give it a unit. Let's say this is 5 seconds, comma. Instead of 8, this is the y-axis. The y-axis runs up and down. This is displacement. The standard unit for displacement is meters, so 8 meters. So now we have something better than what we had previously, right? 5, 8, whatever. But this is something real. This is 5 seconds, 8 meters. So this is some object which at 5 seconds was located 8 meters from a reference point, some given point. We can call that the origin. Okay, and that would make this, right down, this point would become 2 seconds, again that's the x-axis and x-coordinates are time, comma 4 meters. Great. But what if we put that in here? What would happen? Well, let's see. So I have 8 meters minus 4 meters divided by 5 seconds minus 2 seconds. Oh, okay, interesting. So we have 4 meters divided by 3 seconds. Well, what is that? What is okay, 4/3, whatever. What's 4/3? I guess 1.3 repeating. 4/3, but then it's 4/3 meters per second. So what did we just discover? This is meters per second. That must be a velocity. And that's the big point I want you to see here, is that when you have a this is called a displacement versus time graph. Whenever you name a graph, right, and you'll see this on potentially like ACT when they talk about graphing and stuff. Whenever you name a graph, it's always the displacement versus time. It's always the y-axis versus x-axis. That's the way you'll always see it, at least the way you should always see it. Displacement versus time would be this. And again, I know it's a little confusing because there's an x there, but it just stands for displacement. So displacement versus time graph. When we have a displacement versus time graph, the slope of that graph is the velocity, right? And that must be true because, like, look at this right here, right? If I remember the equation we said for slope was delta y over delta x. Okay, well, let's replace that with the actual units. This is the same thing as the change in, sorry, I'm running out of space. Whatever, I'll just write here. Hopefully you can see. The change in, what's the y-axis? The y-axis is displacement divided by, what's the x-axis? The change in time. Well, this is, that right there, that's the equation for velocity that we had. The change in displacement divided by the change in time. So you can see that these things are the same. And that's the point made here on this slide. Here. So on displacement versus time graph, the slope is the velocity. So if I had a question and I said, okay, I imagine you had a quiz or whatever, and the question was, what is the velocity between 4 and 8 seconds? Well, you can just look at this line here and you can tell already what is the slope of this line between 4 and 8. It's got to be 0. And you can do the math and you'll get that, right? Because you would have 6 minus 6 divided by 8 minus 4. And you would get 0 divided by 4. So likewise, you can find the slope here, right? You can already see immediately the slope, right, which is the velocity, is the slope is negative, which means the velocity here is negative. The slope is positive, it means the velocity here is going to be positive. And you can find the actual number by just doing 6 minus 0 divided by 4 minus 0. Okay, so I guess ignore the part that's spelling there. What's the velocity of the object between 4 and 8 seconds? Again, you have a couple options here on how you want to do this, right? You have a couple options. You could do, so obviously we're looking at between 4 and 8 seconds here, so that's this point, like from here. I'm not going to be able to draw like one. Anyways, we're looking at just between these 2 points. What is this velocity between here? So to find that, it's relatively simple, right? We just find the slope of that line. And again, it's the exact same equation we had previously, right? So the final displacement minus the initial displacement divided by the final time minus the initial time. Well, we can already check and say, okay, well, this should be negative, right? Because it's a negative slope, we should get a negative answer. Let's see what we get. So the velocity here will be 0 meters minus 4 meters divided by, make sure I'm doing this right, sorry. It's y2 minus y1, yeah, xy, okay. I'm telling you, I always get it mixed up, so I usually have to write it out like that. Okay, so it's y2 minus y1. Oops, see, I messed up. I thought I messed up. I'm not going to edit it, right, because this is natural. Everybody should make mistakes. This is how we learn, by making mistakes. All right, sorry. So 0 meters minus 2 meters divided by x2 and x1 are the times, 8 seconds minus 4 seconds. 0 minus 2 is obviously negative 2 divided by 8 minus 4 is 4. So negative 2 divided by 4 seconds on the bottom is just 0.5, negative 0.5 or negative 1/2 meters per second. That's our answer. So you can find the slope between any of these points. Again, if you're asked to find the velocity, you have a graph, you can just calculate the slope between those 2 points, and that is the same thing as the velocity. But we can also figure out something else from this, right? Let's say, for example, I know my head's in the way. Let me see if I can move it. There we go. Can I be down here? I'll be down here. There we go. Using the data from table below, find the displacement after 120 seconds and X seconds. All right. So this is some just displacement and time data. And we'll notice that, we notice that here, there are many ways you can try to solve this, okay? I'll put myself back up here. There are many ways you can try to solve this, right? You have different options. You can try to just guess, right? You can say, okay, how could I get 5 to 12? I could multiply by 2 and add 2. Maybe that works. And then see if that works here. 7 times 2 is 14 plus 2. No, it doesn't work, right? One way you can figure out if this is, at least if it's linear data, if it has like a linear relationship, we could see what the difference is here, right? We could say, okay, how much is it going up each time? Well, at 5 seconds it was at 12. Right, so it's at 12, and at 3 seconds it's at 4. So 12 minus 4, 12 minus 4, it went up. The difference would be obviously 8. But that was from 5 and 3, that's for 2 seconds. So it looks like 8 divided by 2. So it looks like it goes up by 4 every time. Let's see if that's true, right? Because from 5 to 7, it should go up 2 more times, right? So 2 times 4 is 8. So 12 plus 8 is 20. Yeah, so it looks like it goes up by 8 every time. And a lot of people will figure that out, right? So you could quickly figure out there's an equation here that describes how the displacement is changing, right? It's going to be 4 times the number, x there. But that's not all of the story there, because clearly that's not just true on its own, because let's do 5. 5 times 4 is, well, 5 times 4 is 20, but it's got 12 there. So there must be another factor there, right? To get from, well, we have to subtract 20 or subtract 8. Let's see. 3 times 4 is 12. Minus 8 would be 4. So it looks like the equation is 4x minus 8. Okay, let's see if that's true. Let's just plug in for one of these. Let's do 12. So we have 4 times 12 minus 8, and this better be, 4 times 12, and then you subtract 8. This should be equal to 40. Let's see if that's true. 4 times 12 is 48. 48 minus 8 is 40. Okay, so we discovered there's a relationship here, and we can write the equation as a line. It would be y equals 4x minus 8. Now, this would be our equation for a line, and this could tell us anything, right? So at 120, right, y is going to be, probably going to have to break out the calculator here. Let's see, 4x minus 8. Whoops, I just wrote the same thing. We want to do, for 120, we do 4 times 120 minus 8. Now, I can do this. 4 times 100 is 400. 20 times 4 is 80, so that's 480 minus 8. So it's going to be 472, I think. Okay, but let's put this into context. So we have this equation, right? Y equals 4x minus 8 for this specific scenario. All right, and that's the relationship. And now I can figure out for any time. You give me a time, I can tell you the y, which in this case the y's would be the displacements, right? These are the y values, and these are x values. You now notice x is always pretty much going to be, your time is going to be on the x-axis. So, anyways, so that's what I'm getting here. Now let's see if we can make this more general. So we have some data, which is right. We know this equation y equals mx plus b, and we also know that when we take a displacement versus time graph, right? So just in general, it's going to be displacement versus time. Put a little vector hat on it so you know it's displacement versus time. If this is a graph, right, and we have like a line, and we know that this is linear data works. And again, I can tell you already this works as long as there's no acceleration. If we have a constant velocity, you're going to get this just a line. right? And that was kind of one of the big takeaways, something you might want to write down when you have a displacement versus time graph. As long as the object is not accelerating, its motion is going to be a straight line. It could be positive line, it could be zero straight across, it could be negative, but it's just going to be a straight line. There's not going to be, the slope is going to stay the same because the velocity is going to stay the same. So what happens if we translate that, right? So again, this is our y-axis. This is our x-axis. Okay, what would happen if we tried to correlate what this is, right? What this is to a real life scenario like this, like a real object that's moving, I should say. Instead of y, right, what's on the y-axis is displacement. So the displacement is going to be equal to slope. Well, we just talked about this. What is the slope on a displacement versus time graph? Well, it's velocity. So I'm going to write velocity times x, which is, again, x is usually the x-axis here is time, and that's going to be happening a lot. Velocity times time. Plus, we have to add this little extra thing. So what does this represent? Well, in math, hopefully you remember that b represents sort of that, it's the intercept. It's the y-intercept, where this intercepts with y at 0. So when x is 0, this is where it intercepts. In this case, that y on the y-axis, that's a displacement. This would be like your initial displacement. Okay, and this is the equation we get. And this is going to be important because this tells us, what this tells us, this equation tells us, I can calculate the displacement of an object as long as I know its velocity and its initial displacement. I can calculate it for any amount of time. Doesn't matter how long it's been going for. And you could do it graphically as well, right? It's all the same. So hopefully you see there's a lot of interactions and sort of commonality between those. Let's put this into practice. A car begins 30 meters south of a stoplight. The car has a velocity of 2.5 meters per second. What is the displacement of the car after 20 seconds? And you know what I didn't do? I'm pretty sure I did not make this slide, so that's my bad. So here we go. You get to see it happen in real time. You get to see that I have to go out to see crop. All right. All right, so let's put this into practice here. Car begins 30 meters south of a stoplight. The car's velocity 0.5 meters per second. What is the displacement of the car after 20 seconds? So let's apply the equation we just used. Displacement is going to be the velocity times the time plus the initial displacement. In this case, not a lot to put in here, right? The velocities, and as long as you know your units, it's really easy to find. 2.5 times 20 seconds plus what was initially began 30 meters south. Again, this is displacement as a vector, right? Displacement is a vector, so that's got to be negative 30. And velocity is also a vector, and you'll see that. Okay, so x is going to be, I guess that's 50. 40 plus, 50 minus 30, 20 meters. But notice, so that sign is positive, so really it's just 20 meters north is the displacement after 20 seconds. And again, this is just 20 seconds, right? And that's kind of what is powerful, right? I could write this sort of like, right, I could say this is the displacement for this car at some x value of time, at some unknown time, is going to be 2.5 times the time in seconds, of course, plus the initial displacement, which in this case is negative 30. So this equation, right, this linear equation, this is a line. If you put that into your calculator and graph it, you'll get a line. It's got a positive slope, but it intercepts at negative 30. This describes that object's location at any time. I could find it 100 years from now, right? If it's still going at the same speed, didn't change speed, I can calculate, convert 100 years into seconds, put that in for t, and I know exactly where it is. And that's a pretty powerful thing that we can do. Okay, I think these are pretty straightforward. I'll do one more example with you. And again, of course, I'll have to make it because I don't know why I didn't prepare these slides, but I just forgot to, I guess. Okay, so here a car begins 15 meters north of a stop sign. Car's velocity of negative 14.1 meters per second. What is the displacement of the car after 12 seconds? All right, so once again, we're just going to start with our equation. The displacement is going to be equal to the initial velocity times the time plus the initial displacement. A lot of times I put xi here so you know that it's initial. It's like, where did it begin? All right, so this is going to be, in this case, the displacement is going to be, velocity is negative 14.1, which means, of course, it's going, we're talking about north-south here, so really it's 14.1 south, times the time is 12 seconds, plus initially was 15 meters north, so it's positive 15. Now for this one, I am going to use a calculator. Not quite so bold. 14.1 times 12 plus 15. Oops, I already messed up. Negative 14.1 times 12, that's okay. Why do we make mistakes? So we can learn from them. So I get, for my final answer, negative 154.2 meters. So obviously it's south, so 154.2 meters south is another way you can say that. And once again, we have this generic equation we could write, right? We could say, and this is going to become very important in our second unit when we talk about projectile motion, right? This object's displacement at any given time, you can think of this as a function. Sorry, let me rewrite that. The displacement as a function of time is going to be equal to, for this object, it's going to be negative 14.1 times your time, and again, that has to be in seconds, plus 15. So there you go. That's a function. That's your equation. Yeah. Okay, that's where I'm going to stop. Again, there's a lot to this, so hopefully you can kind of follow along with what I'm talking about. You did some graphing over the last couple days, so hopefully you can kind of see that relationship, at least for displacement versus time. We're going to talk about what we can find out from a velocity versus time graph soon. I did have one more little question, last little multiple choice here. A snail is crawling up a vertical wall at a constant speed. Which displacement versus time graph would best show this motion? Okay, now you should, based on what we just talked about, know the answer to this, right? Because if we have an object is moving at a constant speed, sorry, I know I'm a little bit in the way, I'll just hang out here. A snail is crawling up a vertical wall at a constant speed. So which of these shows a constant speed or a constant velocity? Well, remember, velocity is slope. So which of these have a constant slope? D here, right? This one? It doesn't have a constant slope, right? Its slope is actually changing. We haven't got there yet, but this would actually represent a changing slope. Remember, slope is velocity, a changing velocity. So what do we call a change in velocity? We call that acceleration. So D here would represent actually an object that's accelerating. Not the answer here, because we want a constant velocity or constant speed. A is a constant speed, right? But what is that speed? What is the slope here? Well, the slope here is 0. It's just perfectly flat. So this can't be the answer because 0 slope, it's not moving at all. This would represent a snail which started maybe like at one point on the wall and stayed there. B is my favorite answer because B is undefined, right? It doesn't mean anything. It doesn't have any kind of physical significance because it's an undefined. Think about it like this. This is what B represents. B represents this at the beginning, like where's the snail? The snail's nowhere. He doesn't exist, right? He doesn't exist here. At 1 second, oh, he still doesn't exist. But then at 2 seconds, this glorious interdimensional snail being exists in all places at one time. And then at 3 seconds, he's gone again. So this represents some sort of cosmic interdimensional snail god who graces our universe's presence for just one brief moment of euphoria, and then back to the dark abyss he goes. C is the correct answer. And C is the correct answer because it just has a constant slope. Simple enough, right? We don't know what it is. We can't calculate because we don't have any numbers here, but that's okay. We know that it is a constant slope. It is a positive slope, so this will represent him going up the wall. So again, his displacement up the wall is increasing as time goes on until eventually, I guess, he gets to the top of the wall, hopefully. Okay, so again, it's a lot of different concepts, a lot of math involved, a lot of things that you have used before, right? Like you've talked about the equation for a line in math class, and maybe you thought, how is this used? Well, you may not think it's useful or whatever, but it is used, right? We just used it. We just used the equation of a line to predict where an object will be in the future, given that it's not accelerating, it's moving at constant velocity. Now, we are going to be able to predict where an object will be in the future if it is accelerating. And that will actually use a quadratic equation. So once again, something else, you may say, well, when I'm going to use, ax squared plus bx plus c, when will I use that? We're going to use it pretty soon. So all these things do get used, and it just is a lot of times the pattern that happens is mathematicians just create or discover something, no one thinks it has any use, and then physicists usually say, actually, we would like to use that. So hopefully this all makes sense. As always, please make sure you contact me if you need help. Thanks.